Hello and welcome back. And we're going to continue our discussion on tangent functions. And today we're going to talk a little bit about the properties of the tangent functions. And let's speak about the domain a bit. The domain is a set of all real numbers except odd multiples of pi over 2. And the range is a set of all real numbers. Okay? And then, of course, number 3, the tangent function is an odd function as the symmetry of the graph is with respect to the origin. Now, the tangent function is periodic with period pi, and the x-intercepts are those things coming from negative infinity to these values of negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, and so forth and so on, all the way to positive infinity. Now, the vertical asymptotes, though, occur at x is equal to what? These values, though. That the graph itself, or the lines of the graph, is going to get closer and closer to these values here. Because these values are basically not included in the domain. And we'll see that in just a second. Important notes about graphing the form, which is a tangent function with a form where y is equal to a times tangent omega x plus b, and also we're going to talk about cotan as well. Y is equal to a times cotan omega x plus b. Now, few little notes about this is for the tangent function, there is no concept of amplitude since the range of the tangent function is from what? Negative infinity to positive infinity, which is a set of all real numbers. Now, that's very, very important now. There is no amplitude in the tangent function, and we'll speak about it a little bit here. But the role of A, however, in this y is equal to a tangent omega x plus b, it provides the magnitude of the vertical stretch. That's very, very important. Make sure you get this down or copy this down, get a nice shot of this. It's because people mistake this and say, okay, the tangent function has an amplitude. No, it's the A actually plays a different role. It provides the magnitude of the vertical stretch. Remember that. It's very, very important. That's a good test question. The period of y is equal to tan x is the period. Remember the period? Is pi. So the period of y is equal to a tan omega x plus b is what? Pi over omega, caused by the horizontal compression of the graph by a factor of what? 1 over omega, this value here. Remember that from the other functions, right? Finally, the presence of b indicates that there's a vertical shift. So a vertical shift is required in this thing. So if you go back to your college algebra days and taking algebra 2 in high school, basically when you get into horizontal and vertical shifts, you understand that number or that value on the outside of the parentheses of that particular expression signifies the vertical shift, whether it's positive or negative. So let's look at the graph here a second here. We have graphing the function of the form y is equal to a tan omega x plus b, and we want to graph y is equal to 2 tan x minus 1. So we want to use the graph to determine what? The domain and the range of y is equal to 2 tan x minus 1. So look at this here. We're going to start off with the basic function y is equal to tan x. So we see the period, right? The period here for this function is pi, right? See, this is pi. So you see the nice little flow here, right? Nice little flow. This has a very distinct pattern, if you will, if you see, right? And this goes all from negative infinity as it does all the way to positive infinity. Now let's look at this when we multiply by 2. When we multiply by 2, there's a what? A vertical stretch. There's a vertical stretch by a factor of 2, right? So look at this right here. Right now, it kind of reminds you of this other word we used A as in for the cosine and sine function, but like we said before now, for tangent functions, right? We're talking about A being a role of, you say, providing that this thing is a magnitudinal stretch. So the A acts as a role, this 2 acts as a role to provide a magnitude of vertical stretch. So that's very, very important. Remember, this is not the amplitude. No. It's not the amplitude. This is the magnitude in which the graph itself is stretching to a point. It's giving it a vertical stretch. So let's look at when we subtract 1 vertically, well, there's a shift, and we go down what? 1 unit. We're subtracting 1. So see that right there? So we were subtracting. So this kind of, originally the graph, of course, was here, and of course we stretched it. And now here what we're doing is we're going down 1. So here's that point, right? From here, or as we say when we stretch it, it's going to be from this point of -3 to what? This point of +1. So you always read the graph from when you read in the bottom, from bottom to top, and also from what? The left to the right. So as we see, it, of course, from -1 to 1 here, and of course when we stretched it, it was negative values in between -2 and 2, and now when we subtracted 1, it caused a vertical shift, right? So here, that caused that to move down, right? Move everything down. So that is from -3 to +1. So the domain here of y is equal to 2 tan x minus 1 is the set of all. Now let's read this. This is a set builder notation technique. You remember that? The set of all x such that x cannot equal some integer k times x divided by 2. And when we say k is a non-integer. And the range will be the set of all real numbers. And now it'll be from -infinity to +infinity, if you will. So let's go look at another problem real quick. So let's go over here. A tan omega x plus b. We want to graph this time y is equal to 3 tan 2x, right? Use the graph to determine the domain and range of y is equal to 3 tan 2 times x. Well, 3 tan is 2x. Solution. Show the 4 steps using transformation. Okay, look what we have here. So we have y is equal to tan x. Then we have the basic trigonometric function here, graphing this. All right? And so here we go on and we're going to what? We're going to multiply by 3 to get the vertical stretch, and that's by a factor of 3. So you see, of course, this is a magnitudinal stretch. It's the magnitude of this thing that stretches here and there, right? From this point to this point. So, like again, I said, I highly emphasize tangent functions don't have amplitudes, right? So remember that. And as we replace x with 2x here, here we go again with our horizontal what? Compression by a factor of 1/2. Very, very important. We talked about calculating this in the earlier videos when we had the cosine and sine functions. Right? So let's look at the domain though. The domain of y equals 3 tan 2x is, here we go, the set of all x such that x cannot equal some value k times x over 4. Again, k is an odd integer. And the range is the set of all, what? Real numbers. If you notice, and this is very important, in figure C now, let's go back to figure C for a second. The period of y is equal to 3 tan 2x is pi over 2 due to the what? Due to the compression of the original period by what? By a factor of 1/2. And notice that the asymptotes are what? Negative pi over 4, pi over 4, and 3 pi over 4, and so forth and so on. And due to the compression of this thing. Now, of course, didn't want to neglect this graph. No, wasn't trying to neglect that at all. I just wanted to hit that spot, hit that point that after we looked at this here, we see the magnitudinal stretch here. Then what we did here, when we go over here now, when we talk about, we're talking about the factor of 1/2 here, see? So when we're calculating horizontal compression by a factor of what? 1/2. And of course, like I said before, as I repeat, we showed you how to calculate this in earlier videos. And if you need me to recalculate these or review this, of course, send me an email or get in touch with me, and we'll do some more videos on that. Okay, so that concludes the portion on tangent functions, right? Now we're going to talk about cotangent functions. And cotangent functions are very, very important, just as well. And we can obtain the graph of the cotangent x, just like we did with y is equal to tangent x here. And so, because the cotangent functions are not defined at integers with multiple of pi, we will focus on this interval though, from 0 to pi. And of course, the table, you develop a table, and developing the table will allow you to graph some sort of partial function of that, right? Partial function showing you how to actually graph the cotangent function or the line. So, but we're going to really get into detail of that also as well, show you some nice pictures of that. So, as x approaches 0 but remains greater than 0, the value of cosine x will be closer to 1, and the value of sine x will be positive and close to 0. Hence that the ratio of cotangent, remember this ratio here? Cotangent x is equal to cosine x over what? Sine x will be positive and large. So as x approaches 0, with x being greater than 0, the cotangent x approaches infinity now. And this is how this will look. The limit of cotangent x as x approaches 0 from the what? From the right-hand side is going to equal to what? Positive infinity. Similarly, as x approaches pi but remains less than pi, right? The value of x will be close to -1, and the value of sine x will be positive and be close to 0, if you will. So the ratio of cotangent x is equal to cosine x over sine x will be negative and approach negative infinity as x approaches pi. So here's how this looks. The limit as of cotangent x as x approaches pi from the left-hand side, x will equal to negative infinity. Now I want to show you some pictures of the cotangent function.